Did the file run? Cool. Oh, hate this Spark. I gotta get a new one. I cheaped out and got like a $25 one. It doesn't, it's not worth it if I die. Yeah, I got it on Amazon. Yeah.
I got one on Amazon too.
Didn't work? Well, it worked for a while and then it didn't work. Yeah, I'm gonna buy an official MacBook charger, so that'll work. But for a while. Get a new Mac? Just buy a new Mac.
You deserve it.
I deserve it.
Yeah, with all the Bitcoin,
You're right, yeah.
Just one Bitcoin will do it. Like 10 max. Come on.
And
buy
Mac.
for Gold Plus.
Max. Or you could wait 10 years and then I could buy everyone a house.
Wow.
Right? Yeah.
But you're not going to do that.
Mm.
I'll wait. 10 years, that's it.
Oh, 10 years.
That's
Well, not in San Francisco, in Kentucky.
Okay, where? Kentucky?
Kentucky, yeah, Kentucky. Or if Kentucky blows up, then meaning like the tech scene blows up in Kentucky, then somewhere else. Because
I'll go with the Mac.
yeah, go with Mac. Okay. She's like, look, Pavon, I don't believe in it. I'm not buying the Bitcoin future.
Just one Bitcoin and you can get it. Like everyone.
Oh, 08 we didn't do. We did 07. Well, we had like 3 or 4 minutes for 07, but I'm glad it feels familiar because we did go over this. We did go over scaling. Well, we went over scaling in the very beginning. No, even before that, we went over scaling. But like binarizing data, scale using min-max scale.
That was just the theory but classifying the data, what is with categorical data, that we did in the housing example.
Yeah, yeah. Mm-hmm. Oh, come on. Saturday we have a speaker, guys. Remember Dell, the CTO, Dell Big Data. All right, so you might want to read up on him. You can look on the syllabus. There's a LinkedIn link. You can check it out. Come with questions. Maybe find out what his favorite color is. I don't know. He's really excited. So.
Did he say what he was going to talk about?
I have no idea. I mean, he's the CTO of like a big data consulting company. So like they It's so weird that Dell went into consulting. I guess it's like IBM going to consulting. But I mean, like, I'm curious about like what they're doing. Like, who are they consulting for, and what do the projects look like? And
Yeah, I'll just ask those.
okay.
Yeah. How many questions do you need?
I mean, like what do they do on a daily basis? Like what's their day look like? Things like that. I'm really curious about those kinds of things. Like how often are you presenting to people? Like, are you working for the marketing departments usually, or you're working for like the programming, like the engineering departments? Like, I have a feeling that a lot of people are just working for marketing departments. I have a feeling that that's what the case is. Because those are the people that have money to spend. Engineering departments have money to spend, but they have money to hire usually, not like to. Yeah. I'm just really curious about who hires them for consulting, all of that. Next week we have Facebook, so mark your calendars, come in.
What are presentations?
December 16th. Well, I hope so. That's the whole point.
He's coming
He's coming next Saturday, December 9th.
with our presentation.
December 16th, yeah. Well, I hope he comes in then. I'm gonna ask him to come in. Oh, Teddy, we're doing O8 data processing from the last class. All right, guys, 15 more minutes. 6:55. Our first thing we ever did was logistic regression, right? Gradient boosting? No, we did a logistic problem. We did a model with logistic, right? Logistic stuff? No? Okay, maybe not. I'm pretty sure there's an example somewhere.
Oh, maybe it was diabetes. Is that the one?
Diabetes. Yeah, the Indian diabetes thing. Yeah. Can you find, if you're done, can you look at that? Just let me know what exact model was used. Thanks, guys. Because we're gonna come back to that right today. I rode my electric longboard from Kickstarter. I had my girlfriend like spot me just in case, and thank God she spotted me, because as I was going, I went past this retirement home, and all these like old people started laughing at me, and I was like, "Huh, that's weird that they're laughing at me. I guess I look funny or something." But my girlfriend was running after me. The wheels came off.
Oh my
I didn't even notice. That shows how oblivious I was. But it was crazy because I was still standing. I was still going. Well, she was like just watching from a distance, just making sure like nothing wrong happened. And she chased after me and told me to stop. It had 4 wheels, but one of the wheels flew off. Because I guess, yeah, I didn't even notice. I guess like I don't know. It was fine. Like, I guess if I turned, then it would have been an issue. But I was going straight forward. So I guess I was only turning left during that time. I don't know, man. It took me so long to get this. It took me a year and a half to get it off Kickstarter. I'm gonna contact them and ask them if I could, I don't know, fix it.
Which one is that?
It's called a leaf board. And it was like $300 compared to like the $2,000 ones. So I was like, all right, I'll just do it. Yeah, boost. So I guess this is why you get boosted boards, because they'll stay together. That's important. Yeah, I wanted to know what model. What model do we use for the NVIDIA data set? Okay, cool. There's regression, not classification. All right.
Oh, okay. I was thinking but they're just converting. They're just waiting. It's from Saturday.
Oh wow, you got the dates down too. Organized student. Or about 10 minutes. Going through it with your partners. Standard scaler is like the typical one you use to pre-process data for neural networks. So that's the one you typically use. So -1 to 1, that standard scalar thing. Take your data set, convert it to -1 to 1.
How do you know which one to use? Because it's like if you know your data, use standard scalar. If you don't use min-max, but what does it mean? Like, what do you have to know about your data to decide?
Just generally for neural networks, you want it between a certain range, so that the differences don't impact each other.
Is neural network the same as deep learning?
Yeah, same thing. Neural network is deep learning, and it's actually, you've already done it. The matrix factorization stuff. Yeah, so you guys have already done it. You guys didn't use a neural network library or anything, but you'll see the similarities. You guys did a subcategory of it already with the matrix factorization. It's nuts because like Amazon was doing all this in 1999. Netflix was doing this a long time ago. Like the stuff that rating system you guys did is the reason why Netflix is. That's how their rating system works. They use matrix factorization, and then the ML stuff you guys did. I mean, that's how Amazon was able to recommend products back in 1999. I'm not sure what they use exactly, but that's what they did.
So when we have data set, basically it's categorical, convert it to binary form, and if
Use hot encoding.
one part
Hot encoding, right? Yeah.
is not necessarily binary, but you can categorize into numbers. And
If it's only 2 categories, then maybe you could just turn it into a binary thing, right? But if it's like more than 2 categories, then you might want to have.
It should not have a max limit, right? I want to do something.
If you had, let's say you had 1,000 categories, then you got a problem there. 100, that still is a problem because then you would want at least 1,000 data points, right?
I have 150,
150. Okay, then who cares, right? As long as they're spread out for each category. So if each category, I mean, they will be, because you wouldn't even have that feature if you didn't have at least one, but you want to have 10 at least for each one. Yeah. I mean, but that's just arbitrary. It's like that's just like a good practice.
Yeah,
And maybe your model just works. Like,
my model score would be worse, but at least it would work.
yeah.
And how do we decide that for what kind of data we want to scale it or normalize it? Because I understand
Okay, so-
categories.
Oh, so like there was, remember that example? Remember that example? And I'm taking away time from you guys, but like that example where the MSE was 4,000. It's literally the reason why the MSE was 4,000 is because we didn't scale it. If we scaled it, then we wouldn't have had that huge of an MSE, right? Because like the R2 score was actually not that bad. It was like a 0.6, and then all of a sudden the MSE is like 4,000, which is like ridiculous. But if we scaled it properly, then we wouldn't have had that issue. Of course, when you get your answer, you have to unscale it. Well, let's say you scale everything, right? Then you would have to unscale your answer afterwards.
After the MSC.
Yeah.
Because I'm getting an MSC of 99,000.
Yeah, then you should probably scale your data.
But then that's my question is, what will I scale it? Because
Just choose one. Just choose one of
I
them.
will scale the features or my target.
Both, everything. Scale everything. Yeah.
So
Yeah.
my entire data frame that I select for my model.
Scale the whole thing. Yeah.
And then I distribute the features like X and Y.
But then make sure you unscale it because the answer won't be like, right? If you're doing housing prices, you don't want 0.7. I don't. You undo the form. Off the top of my head, I don't know. Look it up.
But there's another function.
There should be another function that unscales it. Yeah, should be. Like 2x minus, if your formula is 2x minus 2 equals whatever, then you would do +2 divided by +2 and divide the whole thing by 2. Right? You just reverse all the operations.
We don't have that in the processing sheet.
It's not in our processing sheet. Alan, can you look up how to unscale data using Scikit? Like maybe look at standard scaler, the standard scaler documentation, and see if you could unscale it. All right. Let's see here. All right, so let's take a look here. You know, right, we're gonna import our libraries like we always do. We're gonna use this specific CSV, load it into a pandas data frame, check the first 5 rows. Now can we make some observations about our data? Let's go to Andy, Daniel. Now that's good. We have some labels at the top: gender, age, size, weight, and anything. So we have gender, we have male, and we'll probably have female if we look at other things. And then age. Do you see anything weird about age or different about age? Yeah, so maybe it correlates, but it's also a string, right? It's a string. So that's something we might have to deal with, maybe with hot encoding, or like maybe we, convert it to something else. And we have the size, we have the weight over there. Okay, so let's go down. So we have our data frame in a brain variable over here. And here we're gonna, if we take just the gender, age, and size into X, and then for X our input, and then Y would be the weight. So can we determine what the weight would be based on the gender, age, and size of our brains? So weird. No, not weird, but it is weird. So then what about this? I mean, this shouldn't be that bad. Let's go to Johnny. John, what are we doing over there on print x.shape and y.shape? Why is it? And then why are the tuples like that? Yeah, why is a series? And so it's one column of 237 rows. It's all of our output, right? And then X is 3 columns of 237 rows. It's all of our input because it's gender, age, and size. So we're just splitting it up so that we can, later on feed it into our model. Did this go in? Did this file split it up into training and test? It did. Okay, good. All right, good. All right, so over here, what step? Apparently, pull up the machine learning steps for you guys. Yeah, you have all these. Or I thought I had them. Okay, here we go. So this next part is going to be one of the steps here. We picked our features. I mean, we have our data. There we go. Okay. All right, so over here, what are we doing here? Let's go to a new Angela. Excellent. We're choosing the predictive model. So we're in step 7 right here. Choosing the predictive model. I guess we're going to do this later. I'm skipping ahead. What did you say? Oh, this was just Markdown? This wasn't code? Oh, that was a slide. You're right. Okay. All right. Label encoding. So we're going to take those, we're going to take gender. And then let's see, what are we going to do with gender? Let's go to Johnny. John, what are we doing over here? We're kind of like binarizing it over here, right? Because we're just turning it into 0s and 1s. Essentially, if we did the one hot encoding, then we would have is male 0, and we would have the Boolean of 0, 1, and we would have another column called is female, right? Yeah, and I guess that would be really helpful if we had 3 categories, right? If we had more than 2 categories, then that's when that would be helpful. Yeah. So that's what we're doing over here. And we're just taking a look at what the data looks like. And that's why we see a bunch of 1s and 0s. And anything alarming about this, or does it look fine? Looks fine. I mean, it's not shuffled. That's we did miss that step over here. We didn't shuffle the data. That's important. Another thing is like we want to make sure that there's an even split between genders, right? So to not give any bias in our learning for a model or training for a model. So it looks like it's similar. I mean, you'd have to do maybe a value count or group by and then a count to really get the numbers down, but it looks like an even split. It kind of looks like, what's 1 represent? Female? Looks like there's more females in this data set than there are males, but that could just be me not looking at it right. Can someone run a group by value counts and see what the numbers are? And then let's go to Chris and Teddy. What are we doing over here? Yeah, we're looking at the first 5 rows. We're putting all that data that we just manipulated from male female into the gender column. So we're replacing it all, right? We're replacing all that. We're off of the label encoder, not off of our model, right? Fit and transform is not the same as fit. It's just another function. So this is off of the label encoder. So we're just taking the 0s and 1s and putting that into the gender column here. And you guys don't have to rewrite your pandas data frame. You can make a new pandas data frame too. You can make a clone of your previous data frame and not modify the original data frame. So maybe that's a better way of doing it. If you're worried about the integrity of your data set. Oh, what would you say? There's more males. How many males? 134 to 130?
134 to
103? Okay. It's not that bad, but there is bias. Ideally, you want like a 50-50 split if you can. I mean, it's not always going to be like that, obviously. I mean, sometimes you just can't get more data. 237, yeah. So here, there's a point here about certain machine learning models being really, really sensitive to integer coding. So that's something to be aware of. Just like the steps that you do over here could completely impact the actual model predictions, right? Or the errors for the model. So this step specifically can impact it for certain machine learning models. Kat, do you think it's Slack out which ones? You could look up like which ones, or you could say off the top of your head, or Slack out like which ones are impacted. For which models are impacted or sensitive to integer coding?
Probably like most algorithms will need to make sure that all your input is actually there. So there's some like decision trees or like random forests where they're okay with like categorical variables. As long as like they are of type categorical, like random forests should be able to share data set.
Cool. So certain ones work fine categorically.
Yeah,
random forests.
Probably most algorithms will want.
Thanks, Kat. All right, so let's go over dummy encoding or binary encoding data. Andy, Daniel?
So there's the
Mm-hmm. Perfect, right? So we're doing the encoding thing, the hot encoding, taking the columns over here and turning it into zeros or ones, right? Probably better if you have 3 categories or more, but pretty cool that Pandas kind of helps you with this in a fast way, right? So you don't have to do a lot of work to call get dummies. And over here, we could call .copy to do a shallow copy of our X data frame. If you want to do a deep copy, I forget how to do that. You just look it up. That's not a deep copy though. If you have a dictionary within dictionaries, then it won't copy things inside of it. If you have like a basic thing, the copy will work. But then if you have things within things, then your copy might not pick it up. There's something called a deep copy also. Just be aware of that. I mean, you'll know because it won't work when you copy it. So yeah, just a data frame with 3 columns. Mm-hmm. That's fine. That's fine. But when you have a dictionary within dictionaries, then just be aware that the .copy might not work. You have to probably use a deep copy. So over here, this is pretty cool. We could take get dummies, pass our entire data set to it, and it'll find any categorical data and encode it for us. Pretty neat. So that helps you significantly with part of the data manipulation step. It's like one line as opposed to like someone who wasn't really good at pandas would take like much longer. To be like a couple hours or an hour or 30 minutes. I don't know how good they are, but for you guys, it would just be like a line. All right, scaling and normalization. Can Chris and Teddy, can you guys go over what's meant by scaling and normalization?
So I guess it's saying that some algorithms will perform better when the data is normalized. So you're taking your data and before, so you took the data and you fit it.
Yeah, we did it with their recommendation engine and like a bunch of other places.
So we fit the data to a certain scale.
Mhm.
So, work with the model.
Great, right? So it'll work with the model better if you scale it first, right? And if you scale the Y, then make sure you unscale it. Yeah. Alan, were you able to find how to unscale something? Okay. All right, so here we're splitting. We're going to take our data and turn it into training and test, and then John, you mentioned it was like 75-25. That's what the automatic. That's what the split was. So it's going to split up our data. Basically, what this is going to do is return a tuple, right? And the tuple is going to have 4 things in it, and those 4 things are going to go into these variables right here. And so we have our X training, which should be 75% of our data, and then 75% of our output, and then 25% of our data into X test, and 25% of our output into Y test. And then we could take a look at X train.head, or we could just do, probably a better thing to do would be, I guess I can, X train. All right, so 75%, 25%. Does that look right? 25%. Len X test divided by len plus, or you could just, you could put T37. Yeah, that's good. So that's 25%. All right, standard scaler, right? We're primarily going to use for our neural network stuff. So few options to call on people, but go ahead, guys. Andy, Daniel, just like you guys. Yeah. And if you haven't gotten to that, you can just read it. Just read it. It's fine. Mhm. Yeah, you basically said it, right? We're scaling it -1 to 1, right? That's where our data is going to look like, -1 to 1. So let's take a look at what xscaler, what they look like right here. So I'm going to just do few. Okay, X train scale. Let's see what that looks like. And we see, oh, interesting, it goes above negative, it goes above 1 and -1 a little bit. Interesting. I thought the max was was 1 and -1. Kat, do you have any insight in that? Like why it's 1.15, not 1 or -1? Standard scalar, yeah. Maybe there's a bias. No, there shouldn't be. We didn't add anything.
So it could be negative. So like the mean is centered
Mhm.
around 0. And the standard deviation is 1.
Got it.
So you would just have most of your values.
Oh, most of the values will be -1 and 1. Yes, about like, so in a standard normal distribution, it'll be like 65% of our data. Got it. Okay, cool. Perfect. So then most of our data should most of the time be between -1 and 1 because it's a standard normal distribution. All right, so, and that's what they say right here. All right, let's go over this code here. Well, we can just take a look at the charts instead of looking at the code, right? That's better. Teddy, Chris, do you guys want to go over the charts, the original chart of our data and the scale chart?
Okay, so the original data is very clustered together.
Mhm.
And all above 0. And then when we scale it, with our training, when we scale it, then it's reaching down below 0 and it's spreading out.
No, great observations, right? It's really clustered together when we have our original data. Oh, Teddy, were you going to say something?
No, I was just saying, let's just get it. What we did original, what other
Oh, perfect. Great addition. So Chris mentioned for everyone online that this was really clustered here, and it was only above 0. And this one, it's -1. It's negative and positive, and then it's more spread out. And then Teddy mentioned that this is a standard normal distribution, and that it's centered around 0, and that the standard deviation is 1. Standard deviation is 1 for this plot right here. So that's how the scaling of our data impacted our data. And then going down here, we have min-max scaling. So min-max scaling takes the minimum of our data set and the maximum of our data set, and it scales it between 0 and 1. Right? Okay, cool. Let's take a look and see if it's what it looks like. So we'll try xtrain min-max right here. Scroll up. And we see our data set. You see the highest it goes is, well, we don't see, where's 1? There should be 1 somewhere. Yeah, here we go. There's 1. So what does 1 represent? Go ahead. The max, excellent. And let's see, there should be maybe a 0 somewhere. 0, what does that represent? You can speak louder, Johnny. Min. It's just like, it's just us, 6 people, right? You can say anything you want here. No one's gonna judge you. All right, so we scaled our data like that. And then let's take a look at our chart. So let's go to Andy and Daniel. What observations can you say about our min-max scale data versus our original data set? Pretty different, yeah, nice. It was like 237. Yeah. It's like even hard to see. It's like hard to tell that there's 237 in our original data set. Easier, a little bit easier to tell with the min-max, but much easier to tell that there's a lot, that there's 200 plus, that there's scalar. So we see our min is at 0 right here, and our max is at 1 right here, and then we have our data in between right here, right? As opposed to everything getting clustered right here, and our min, this is our min, that's our max. We're taking this point and throwing it right here in our origin, and taking our max and putting it right here, lining it up straight up with the 1 right here. And this will also help us when you look at the MSE. If that's what you're going to use, the MSE will come out a little bit better when you scale it like this. And like I mentioned before, but generally you're going to use the R2 score for all your models, right? When you use dot score on your model, it'll default to R2. So you're looking for an error close to 1. Yeah, go ahead, Johnny.
So back to that, like this password here, is the Y value output, so like brain size?
Yeah, this is the brain size.
And
And
X is just everything else.
X is whatever we passed in here. No, the Y is the weight, I'm sorry. What did you say? Brain size, weight, sorry, yeah, weight. X is size. X is the three features. Yeah, exactly. Scaled. All right, so
I have a question. So when that question you originally asked, like, what can you tell from the data? Like, what kind of things would you look for someone to say, like, in this? Like,
on an interview, like the normal distribution, it's more like you could tell that this is definitely not a normal distribution because it's not, you don't see it centered around 0, right? Because you want the, like right here, the mean median, it's probably gonna, looks like it's right here, looks like it's in the center, which is what you see with a standard normal distribution, right? You see the bell curve, the mean median are right here, and then you go out like 65%. You go with 1 standard deviation, and you see the majority of data in there. Go out 2, and basically all there. Right? It's like 95% of it.
So in this case, we're on flatter bell curve, or shorter bell curve. Since there's less clustering around the origin.
Yeah, I mean, it'll be a bell curve. This is a perfect bell curve, right? Essentially, because we turned it. We did. That's what it turns it into.
what other things besides distribution?
What other things other than the distribution would you? I'm going to default to my wonderful TAs. What other observations can you guys make about this?
I think the important part of this is really the important part about like scaling your data. That you kind of want your data really all on playing field. Like so for like an example, if I had a column salaries like versus stage. I mean they're just in very different scales. You're trying to find a solution, given those. Want them to sort of like that's kind of really what scaling is about. And you're able to really kind of look at these features. So you want them sort of that same. Like,
If that's like a kind of question, you would do a scatter plot or something, a graph, and say what,
yeah,
Yeah.
that definitely happens.
So I have a question about, so the 2 plots. So one thing I noticed, like it retains the basic stuff.
Right.
Right, but it's spread out. So what do you mean? Right, we're scaling because it might work better than long.
Right.
Oh, Chris, I'm going to add my 1 point, and Cat can go. The MSC, if you did scale it, then the MSC will be more meaningful. And all right, guys, how about you all sit in the front? Come on.
So I think like maybe when we first looked at like scaling, remember when you guys, when I think I sent out that like side-by-side photo of like, yes, you changed the numbers in that column, but technically it was still equivalent, right? Like notice that the distribution, like when I drew the histogram, right? It was the same like general shape. You're just scaling it so that it kind of makes more sense relative to like all other features. So like Chris made like a great observation here. Yeah, you're retaining the same general shape, right? It's still like this like oval shape-ish thing that's this way. It's really kind of about the same spread. The only difference really between these two is, so like this point is still like this point. See what I mean? Like all those points still correspond here. The only difference is, so just like really your axes, right? And you're basically in some ways all your numerical data and all your features when you scale everything. Now they can all kind of fit into this axis. Like as opposed to, let's say you have salary on one set of axes like this. And then when you plot all your ages, they're like over here. Let's say you had another like set of like other features and they're all over here. You see how like your space is just kind of like all over the place? But when you're scaling it, now you could have everything sort of here, right? Because everything will be centered at 0, so that's what like standard scalar does. And then since it has a standard deviation of -1 and 1, so most values are going to be here, right? Just kind of like your, and then you still have all the other values like scale to just kind of where they are. So they're not the same numbers, but they're equivalent, right? So they're not equal, but they're equivalent, right? It's kind of that idea. So technically, you're just sort of transforming your data so that like your algorithms.
So maybe a stupid question, but like
No stupid questions.
for the scaled side, so there's like one standard deviation, right? Is that a radius of 1, or is that just like I don't know how to describe it.
Yeah, it all it just basically says is that that like I always forget, like 67% of your data or whatever is gonna fall within like that.
But,
Yeah.
But now that it's like 2D, would like everything within one radius or one?
Oh, you mean like I see. Yeah, like
Yeah.
here.
Yeah, like would that be considered one
So
standard
it's like
deviation?
two-dimensional.
Well, it depends on what the standard deviation is, right?
Oh
Like,
yeah, but like this case it would be 1.
yeah, I guess like 65% away from the center would be one standard deviation or whatever. And then 2 standard deviations away would be 95% of it. And then 3 standard deviations away would be 99% of the data. So you just draw a circle around, or oval around that part, I guess in this case, and then that would be, I knew you had a question for Kat.
Yes. About what you said depends on what standard deviation is, but I thought when you normalize or when you scale the data, the standard deviation is always going to be 1.
For this particular, the standard scale.
The scale,
Right. It's kind of default
Yes,
mean
for
of 0.
the scaled data,
Um,
that's why we have.
Good question. Yeah. So what, like,
That's why we have 66% of the data.
yeah, right here.
-1, right?
Yeah, right here. So 60%, 65% or 67%. It's going to be around here, and then this would have 95% of it, right? And then another deviation.
The farther you go from the center, the standard deviation is increasing.
Exactly.
Only because in this, I can scale it like 1, 2, 3 only because this is.
Yeah. So this is a scale.
Thank you.
So, yeah. So, but I think it's much more important to be like, not really like making like big interpretations necessarily of just how something's distributed. But again, like the idea really of scaling is that you want your data, I guess it's a normalization process. Like I said, if you're going to compare, you know, like milligrams of, you know, like some kind of maybe drug or something versus, like I said, salaries and ages, and they're so like different scales, right? In order to really kind of make sure that they all are sort of together, you scale them all kind of within the same scaling. So that's the idea. I don't normally look at these and be like, okay, let me make some conclusions about like my data.
It's just
I mean,
for you
that's
guys
just
to
how it
kind of
is.
like look at it
Yeah.
and see what's going on.
Yeah.
It's not like when I asked those questions, it was more to make sure you guys understood what was going on.
Yeah.
We didn't, like Kat said, main takeaways, right? Data didn't change, right? Now it just, you know, the MSC is not going to be big because the MSC is going to be scaled relatively to what your data points are, and everything's a Gaussian distribution now, which is better. Remember I said that when you scale your data to a normal distribution, it's better for your models. That was like one of the first things we talked about, right? Here we are doing that, right? That's exactly what we do using standard scalar.
So what's the difference between the standard scalar and the mixed
And then which one?
You tell me. So you tell me. You know the answer to this. Go ahead. So she'll elaborate, but you just answer your question. Go ahead. The difference is -1 to 1, right?
But that's
For a standard scalar, for the majority of the data.
Yeah.
And then for min-max scalar, the minimum of the data sets can be 0, the maximum is going to be 1. Everything else can be scaled between. Which will be better for certain models.
isn't that the same? Oh no, in the standard it's
It's not, that's not a normal distribution, right? Because the
The
middle is somewhere between 0 and 1. It's probably like, I don't know what it
in
would,
the standard.
in the min-max. In the standard, the minimum, like the mean median is going to be right at 0, 0.
I guess you can think about it this way. There's many ways to scale your data, right? So like min-max is an example, standard scalar is an example. I think there's a normalizer or whatever. They're just all kind of slightly different on like how you want to scale your data. But again, the main idea is the same, right? Like you want all your data sort of in that same like kind of ballpark. No, I don't think anybody can tell you like, okay, you got to make sure you do min-max scalar on this. Usually I pretty much just use like standard scalar. I might, like when I'm tuning my models after, I might change the scaling and see if it improves. But just kind of looking at your data, it's kind of really hard to guess. You almost just like go with, I like I said, usually just kind of go with standard scalar. If I can make improvements on it later, I might try different scaling methods. But there's no sort of like definite answer of like, I'm looking at this is the type of data it is, I'm going to use min-max scaling.
So the difference is again, it's the type, again, it's type of scaling method,
Right.
but min-max would be only between 0 to 1.
Exactly. Like they're just kind of different parameters, right? Like it's just kind of a different way to scale it. So like I think normalizer is you take the maximum, right? And then that's what you divide everything by, right? Or something like, you know what I mean? So again, it's just another way to sort of like scale your data.
You're off, Kat. Thank you.
I know it.
All right.
Yeah.
Take a look at max scaling. All right, so let's put it together. Turning our categorical, well, we used the get dummies thing and then turned, you know, just like before, turned all our categorical data into integer numerical data, split it into training test, scale it, and then plot it. And we also, what step are we doing here? Let's go to Chris Teddy. This line right here. What step is that in our machine learning workflow? Fitting. Yep. Try or starts with a T. Training. Right. We're training. We're fitting our model. We're training our model to our training data set to 75% of our data. And then we're creating a prediction right here. Model.predict. Passing our X test scaled. So over here, we're taking in, or plotting in Y test scaled versus Y test scaled. Yeah. I mean, the blue part is just the predictions is that interesting. This should be X test scaled, right? Yeah, and this should be X. I think I'm a little confused by this. What should these be? Anyone help out? Right, we want to plot we want to plot the data points, all of them, and what the actual values are, right? And then we want to print out all the data points, the x-axis, and what we predicted. That's the red line. So the red line should represent what we predict, what our prediction is. In the blue line, the blue points, how high the blue points are that should be what the actual values are, right? Maybe can you guys play around with it? Just tell me.
So what's wrong with that? It seems fine. I don't see any reason to change anything.
Everything's fine.
I don't.
It ran fine.
Oh, I didn't change it.
Isn't this just a graph?
It's different. It's different.
Well, I don't know, isn't it showing that you a visual between the predicted
Mhm.
and your actual array?
So the
you
scatter
can
plot is,
visually
the
see
scatter
that.
plot is correct. I'm just going to plot this thing.
So there's one.
All the values are reflected. I thought one should be,
But you have to have it on the same scale.
even the X test scale is on the same scale.
Oh, I see. You know, because it's Y test scale.
Yeah, that works. Like, what is that?
Yeah, so if
do
I just run this scatter, it's fine, I understand. It's my X value within the celebration.
Good. It doesn't.
Oh, so that
Mine
makes
is not.
sense, right? Because that's what our test. That's what our
X
actual.
value.
These are what the actual outputs are, and this is what we predict.
Yeah.
Right. So that makes sense. And
No, that was
then Y test scale.
ouch.
The Y test scale and Y test scale
That's
is.
it's in my
Reversing which I know it's kind of weird, but we're showing the difference between the actual results, the actual Y test results, and what we predicted, right? And that's what we're doing. It's kind of weird because we're not passing in X test.
That's
I guess if you try it, pass an X test.
It
See
says
what happens.
X and Y should be same then.
Can you put X test in there?
Try to put
No,
that.
that's
See
it.
what that-
right.
Oh, yeah.
Let's just move on.
Wait.
Let's see. I mean, it shows the difference between Y test and Y predicted, right? I guess that's,
I understand the standard
Yeah.
part, but I don't understand the red line. Plot.
Isn't the red line just like, I mean, it's not the.
it's Y predicted, I guess.
But it's just to show, line of press with the middle. It's like Y test yield and column Y test yield, right? So it's just showing a line. I guess it's showing like one half the data is on the side or on that side. It's not really. Because
Well, it's not. It's not like we're showing that. Guys, forget about that chart. Just forget about that chart, right? We should be charting X test and Y test, and then X test and Y predicted. I mean X test and Y test, and then take X test, pass it to model.predict, get Y predicted, and plot Y predicted versus X test. That's what we should have done. Forget about that graph. Open up 09 and run through that with your partners. It's the same thing, but with a different, should be a different CSV. 09 Stu pre-processing. All right, you guys are going to do that. Let's look over it with your partners for 15 minutes.
Back to the red. It's second.
These are the ones that could be. Basically, even it's one. Index one is a two.
so
So the top one.
So this would be, so let's say this is. So
Seven.
this is actually.
Me too. That's I just saw that tonight. I know it's a map for Stanford. Taylor.
Yeah, I can see that.
So I
Now,
guess
somebody
it's-
just, I wouldn't know what he Yes, and this brings this, that's basically doing the ones. So basically, it's one or. So you magically. Pretty much, it's not used for any other. There's just the variance.
Where did they do your training?
Oh,
I didn't see that.
about the graph.
Wherever the dot fit function is probably.
Did you? Okay. Yeah. Oh.
About 10 minutes.
Yeah, and that's the whole. Exactly. The one that- yeah.
Oh, maybe that's yeah. Next train. No, you want only so you just do just X. Just X test. Yeah.
Good.
It's not. Data. This goes in
But that's just.
you should check the show.
I thought maybe. Here it's.
Oh, you just do sharing. No.
It's you're one.
Okay, well, tell me.
You go first.
Yeah, I think they said like two things, right? Like graph is what we want to say, but you will graph the actual
The chart bottom.
but when we try to graph x, the reason x is the graph is because data is okay, but you could always use working with examples. Since we have like when we
Okay, yeah, because that makes.
if you do diet in the parentheses x, you see that it's like a line. Yes, it's for different x.
So here we're taking the y-test scale. Right here. So see how like before we did scatter plot,
So it's
0 was where it started at, and then like went to standard deviation corrections. So it's like the same deal, we're taking y.
So like, I might end up we had a day where I
But I think the process, I think, is
So
you don't really know what it's gonna come out of your y-test. There's no way to predict that.
So just to give it a small background, I'm just trying to change the scattering.
this much. And the higher it is, the bigger our
I
predictions
was trying to like sell all rows.
are. The bigger our predictions are. As they get,
So
those are set predictions that
I know
are
it's
farther
different
and
than
farther
you won't have any much better.
should.
But it just makes yeah. That's so different. It's totally different.
I guess it's a weird way of representing it. Guys, that graph is weird. Just look at the error, really. All right, look at the test error and training error. That's probably most of the time. A lot of everything.
That's that combination.
Yeah, the number of people.
Sounds.
Well, this is what we want to see. These are predictions. Well,
Yeah, I know.
well, we're going to see how.
All right, guys. We're gonna go on break for 15. Come back, unzip that folder, and jump right into the notes.
Did you just?
Jump right into the notes. Unzip that folder that I just slacked out in activities. We're gonna go on break right now.
And predict. So, yeah. Here's prediction.
Trying to draw
Putting it in
this is my scale. Oh, I want to
just in the environment.
I thought it was going There's no way.
Yeah, I mean, some of that sort of variables impact them. Right, I mean, they kind of be sometimes cool.
So
It's not even a lot of work. If I want to do it, I can. I'll do it.
Yeah, it's probably not a good predictor. I think that's kind of what it's basically. I think it would be useful.
They're like, use some machine learning to figure out this. We make a neural network to figure out the answer.
Like how. Yeah, I think if anything, yeah, just because you have. It's probably not a good issue.
no, it's not.
It's not really. So again. Sometimes you might actually. I'm really not 99% that. So, in some ways, yeah, just be like it. In order to make it. So,
So, let's see. We'll do a much smaller data set. Okay. We'll figure this out. So let's do, we'll do, 95, 92, 80, 70, 60, 59, 1, 2, 3, 4, 5, 6, 7, 8.
They're all really serious.
They're not like 4, 5, 6, 7, 8, 10. So top 0 percentile.
Yeah, so usually.
Where the top 10%, the top 10% will be yes. That's another 10 percentile.
Just on the stuff.
Hey, Kat, real quick. 10 percentile in 10 numbers is the top one. In 10 numbers. Wrong or right?
I mean, you mean like.
The 10 percentile. That's
Sure.
like, just 10 numbers, right? 10 numbers.
I think there's 10 numbers.
There's 10 numbers.
Okay.
Right, so it's 10 percentile. So that's the basic.
So
Right?
that's.
So then if you have the top 50, you can top 50. And you actually, 1, 2, 3, 4, 5, it would be this. So you actually have a top 10%. It's in the top 10%. Right, so in this, so here, this is a top 10%. This is 10 percentile. For this whole thing, right? But for this thing, this is like the top 20. This is the 20th percentile of the 50%. Yeah, so I guess you take the 20, the top 20%, the 50%, and then the top 10%. Right? There's like 1 out of 5. 1, 2, 3, 4, 5. Right? 1 out of 5 is 20%. Close to 22, 120. 1 out of 10 is 10%. Right? So this is the top 10% of the whole base, and this is the top 20% of the top 50%. So if we take the top 20% of the top 50%, if you just scale, if you sort it, you take the first X number. Actually, how many items do you have in the top 50%?
I think there is something.
So,
The housing is that. So.
even the top 50% percentile salary for that position.
It's not like a classical. Exactly. Well, so some elements are like decisions.
Let's look at this. So, I can't do 50 to 70 just this 5. This is 4. And this is 7. Right? So to me, 70 minus 50 is not that long. And then you have like 7. I guess you could create a model, which I don't know. I mean, that's like the one way to do it. Not like that's no, I know. So what's like 50 is 70? Oh, you wouldn't have it. You don't have to like, you don't have it.
steer you towards what algorithms you use.
Yes, let's try to figure it out. So maybe like the difference kind of and how we determine right? It's the 12970. I just think it's up.
So C, these are
The other question I do is that I was
so notice that now it's yeah. Or is it these are kind of like so these are somebody it's gonna be
I know, really,
exactly. Like, yeah, so notice these are all like
yeah.
oh, I see.
Oh, the
Well,
meeting.
It sounds like
Yeah.
so we
Every day.
Right, usually that's like a public school, basically. That could be a decision. All of that. But basically, you're on this You're like, yeah, we'll stop like this.
Yeah.
Don't come back. Give him an answer. Just say instead of 90, like feels like because I think that's knowledge. And then just the whole thing is that easy answers. Remind you to provide.
That's what they do.
Another like idea that I thought was so maybe you could assume that distribution
That you go to the city, but now you have this document. Now you're gonna have to do a little step. That's the other step. But you could see it anyway. So, I would come out of this would be, that's 75. So I can see that the 98% is a little clear. What is that value? So it's a sense problem. So you could, like, again, like, sometimes a lot of these take home, but that's really why. Like, there's nothing wrong with, like, what, like, Lamont said, like, well, hey, I'll assume that, from the data, we'll go with it. And I'm just thinking, okay, well, usually salary is kind of like a normal distribution, right? Some people are compensated a lot more. Some people are compensated a lot more. Most people are that's remember when you did those kinds of stats comments? You're like, so the IT store, somebody down the store, what percent of the student? Hey, this person, what do you think? What percent? That's how you get into the value. What is the value? I mean, what that means. What is that? Yeah. You can get the values. Remember, so it's not quite right.
Okay.
At equal. I think that's why.
All right, guys. Open up the notes I gave you. Open up 00.nd. I slacked out a zipped folder. We have a PowerPoint that was made, but I feel like this is a better intro to that PowerPoint. It's basically the 3 blue, 1 brown introduction to neural networks. I think the guy did a really good job on explaining a neural network and even relating it to the matrix factorization that you guys did earlier. So if you have headphones, you could put the video on. I recommend you just read through the notes. I summarize things a little bit and go through screenshots. I'm going to go over it again, and then we'll go through the PowerPoint that was made for you guys. After that, we'll look into doing logistic regression or logistic classification. Yeah. So go through this with your partners. Have one partner open up the pictures and have another partner just have the text up. And you can always go through the video. The link's right here if you want to go through it again. So we'll do this for 20 minutes.
doesn't see it here.
Yeah, I just it was because like we're just running through the activity. But in 5 minutes, Jake, I'll be back. Four minutes. At 3 minutes. Each layer affects all the layers. Each layer affects all the layers. Like each weight affects all other weights. This is a basic version of it.
Yeah.
I mean, we're using range function. We're use Keras and range function. Well, Keras, you can write tensor. So I'll give a background with tensor queries and Keras and what that does.
No, it's just that this is the like actual vision.
Oh yeah, sure. Yeah, you could use that for actual. Sure.
No, I'm saying that's how actual like how.
Oh, how our eyes work. Oh, I have no idea. You should ask Alan.
Oh no, I know that's how I said this is how.
Or like Daniel. Oh, do you know that's how our eyes work?
Yeah.
Oh, okay.
I was saying, is this based off of that? This is.
Yeah, it's based off. Based off of that. 30 seconds. All right, guys, let's turn it off. You can finish it up at home. I mean, we're gonna go over it. I felt like this was a better intro than we gave. Like, I think you're gonna understand everything a lot better by watching this video and running through what this dude put in, right? So, what's interesting is like taking these pictures, like these 3 different pictures, right? And your brain automatically recognizes that they're all 3s, right? Really quickly. But then as soon as the video was saying, as soon as you make it a coding problem, it gets like much more difficult, right? Like writing a program to take in a picture, break it down by its pixels or whatnot, and telling whether it's a 3 or a 6 or whatever. That's much more difficult. And now I'm gonna pause for a second. Let's go back to our vocabulary for machine learning. Regression versus classification. What's regression, Johnny? Or give me an example. You don't have to give me a definition or something. Just describe it. What's regression? Fitting a line. That's linear regression, fitting a line. Like, what is regression? It's going to give us like we're dealing with a numbers, right? Actual number values, right? They say continuous, but what they mean is like a number, any number, right? That's what regression is. Now, what about classification? Let's go to Angela New. Labels, right? Categories. So when you're dealing with neural networks, right, based on this video, are we doing regression or are we doing classification? Classification, right? We're doing classification. We're trying to figure out what number is this, right? And I know we just said regression is like what number, right? Like this could be dogs. Like, what type of dog is this? It could be. It's just we're looking at an image of a number in this particular situation. I know that's weird, but it's classification. It's classification. That's what we're doing. So keep that in mind, right? That last layer that guy was talking about in the neural network is literally like the numbers 1 through 9 or 1 through 10 or whatever, and then whichever one has the highest number for that neuron is going to be, we're going to assume that that's the classification for it. So, your brain can tell that these 2 numbers are different, right? But a program has to learn to be able to do that. And when I say learn in the video, what did it talk about? Like, what does learning mean? Training, sure, but forget all the language. What about like the formula? Like, what in the formula is learning process? Finding the best weights. That's what we've always been doing, right? Y equals mx plus b. What's the best b? What's the best m that fits our thing, right? Like, that's what we've been doing the whole time. Like, what are the weights? That's it. That's what deep learning is. Optimizing these weights, optimizing there's another one. What's the other one called? It's not the intercept. It's the bias. Optimizing the bias, optimizing the weights so that it basically classifies things the best, right? And it all boils down to the same fundamental concepts of machine learning, where you have your features, right? This is still supervised. This is not unsupervised, right? Our images are going to be labeled. We're going to know that this is a number. It's not like we don't know what these images are at all. Like, we know that these are numbers. What was I saying? Well, you're gonna have these labels. You're gonna have these labels. You're gonna have training. You're gonna have testing. Still, you're gonna still have an error, right? You're gonna still have all of that. Everything you've learned, it still applies. Right now, it's the concept of the neural network. It's funny, but the application of it is actually not that difficult. Like, actually writing the code out for this, it's not that hard. It gets even easier on Saturday. Like, Saturday is even easier than today. Because today we're not going to use Keras, but on Saturday we will. So let's take a look right here. We're not going to backpropagation today, but we will on Saturday. But the learning The optimization of the weights. I don't know if it's a linear optimization problem, but it's called backpropagation. I gotta look up, I have to look up the actual math to see if it was linear optimization, but it's called backpropagation, where like everything's really connected to everything else. Where like you add this layer in, and it impacts all the other things, all the other layers, and all the other neurons. And then when it said neurons, let's see right here. Like okay, before I get into that, this first layer, what does this first layer represent, Andy, Daniel? That first layer right there, what does that represent? Or John, you can help out too. It's the actual number. It's the scale of a number, right? It's going to be either 0 or 1, right? Like 1's going to be completely lit up, 0 is going to be completely dark, right? And we have 784 points over there because it was what by what? It was 28 by 28, right? Well, 28 times 28 is what? 784, right? I wouldn't know that off the top of my head. I remember my mom made me memorize the times tables, and that did not help me much in life. Yeah. Or maybe it did. I don't know. I don't think so. Yeah. But anyways, right, this is our data, first layer, and our last layer is the classification of it, like what number it is. And then we have all these hidden layers right here. And we'll talk about that. I mean, you already went through it, but it's, what are these hidden layers? Let's go to Chris's row. What are they doing?
They're taking the input from the previous layer.
Sure, yeah, that's good, right? Yeah, it's taking the input from the previous layers, and it's going into these neurons, right? And then that input's running through a function. It's called like a Sigmoid function in this example, and it's running through that function, and then it's going to create a number, and then it's going to feed that number into the next layer. Right? I mean, he starts at the beginning calling it a number, an activation number, right? But then he starts talking more about how that's not actually the case. It's more of a function. So each one has like a value passed into it, and there's a function that it runs through. Let's go down. Yeah, remember it was like 0.58 was the number, was how gray, how dark it was, or how light it was. Okay. In layers, we talked about that. Yeah, so over here, so what are these layers doing, right? What are these layers? Why these layers? So he went over on a high level point of view, like what if you break up the numbers into different parts, right? Different parts. So this would be like, this would be that last layer right here. Oh wait, no, wait, one sec. This last layer right here would be like these. Would be these, right? And this is from a high level point of view. This is from a high level point of view, just so you guys have like a framework. Well, because like it's gonna look very simple, but later on when you use Keras, but then understanding what these layers are doing, like why add more layers? What happens if I just don't add many layers? What if I have only one layer? Because you can add as many layers as you want, or you can have only one layer. And then you determine that based on, you'll have an error, right? You're gonna have an error for your training set, an error for your test. And if the error for your test is really high, then maybe you should add some more layers, right? And even before you do a neural network, sometimes for your classification problem, you could use logistic regression instead, just to try it out. Okay, so then you could take these things and you could break them up even further, right? You could break up these things even further, and that's what the previous layers were, right? So you take this circle and you break it up even further, and that's what the previous layers were, right? And then and the training is when you're training, you're basically doing the back propagation. You're optimizing the weights, right? You're optimizing the weights of what, and those weights are basically representing what this would look like. It's trying to figure out what this, it's representing this particular part of the number that was drawn for that layer. All right, so let's go down, right? So over here we saw that there was this picture of the lion, right? So you could see it could be applied to images. I mean, that's what it has been used for, right? Images. And then they even showed another example of using sound, right? Like converting the sound into text. We have the waves. So you could use this for other applications other than just recognizing numbers. Cool. So we have these parameters, right? The weights. And then here, this is a little bit more, this is actually what you guys did for your recommendation engine. This is what you did for your recommendation engine. You had some of the ratings already done, but you had to fill in the rest of the ratings, right? You had to make up all the other ratings. And so over here, we have all these weights. And then they also have like a bias. Where's the bias? Well, go up for a sec, right here. So this sigmoid function. Andrew, do you want to talk about this function right here? Perfect, right? Squishes the values from 0 to 1. And so it's as the farther away, the more negative or positive you go, the closer to 0 or 1 it becomes, right? Like, as you said, squishes everything. And then like in between, when your input is like between 1 and -1, that's where it grows probably the most. Probably grows the most. And this is a function this is like the activation function inside each neuron. Inside each neuron. And then there's also a bias, which they go into, right? So, well, a kind, well, you scale the data beforehand. It's going to scale. It should scale the data for you, from what I understand. But the function that we're using in this neural network, right? And the function we're using is, let me see here. This function. This is a sigmoid function. So it's not linear. It's not a linear. It's not y equals mx plus b, right? But we're using this function right here. Right, and again, this is just an intro into it, into what we're going into. So you're not going to understand everything. Once you implement a few, you'll start seeing everything happen a little bit better.
It's the step of scaling. We're just using a different function.
Yeah, so you take in the numbers, right? And you would scale them like right away, right?
So we're scaling it.
Like the scale here, like, let's not get past what the number represents. What does the number represent? What would you say, Chris? The grayscale, right? Is it really light, or is it really dark, right? If it's gray, then what does that mean? If it's gray, it's an edge. It's an edge. It's at the edge of the number, right? If it's really light, what does it represent? It's the filling of the number, right? It's the filling of the number. So if it's closer to 1, then it's really activated, right? It's like it's the meat of the number. And then if it's like gray, it means it's the edge of the number, the very edge. And if it's black, it means like it's not part. That's like that's beyond the edge, right? That's not part of the number, right? It's really close to 0. So let's not forget what those are the numbers that we're dealing with here, right? That's what the first layer represents, right? That's when it was scaled. That's when it was scaled, and then we're feeding those numbers into the sigmoid function. Okay, so then we have this bias also. Let's not worry about that too much, but it's it's like the plus b. Think of it as like the y-intercept of a linear problem. And then each one has a bias. Every single one has a bias. So that's where, and then they talk about this huge number of 13,000 weights and biases, which is humongous, right? And and then as Angela mentioned before, the learning means like the deep part is having multiple layers. When you say deep, it means having multiple layers. Having one layer isn't deep learning. It's a neural network, but it's a network. But then having multiple layers means it's deep learning. And then learning means finding the best weights and biases, right? To optimize for the problem, to reduce the testing error as much as possible, right? If the testing error is really small and your training error is really small, then congratulations, your neural network is working, right? At the end of the day, it's the same thing as all your machine learning models. The same process applies here, right? And yeah, so it's important. What he was mentioning over here is like understanding this whole concept of what weights should be used. Like if you see that, if that's your image, right? At that point, if that's what your image is, you know it's not zero, right? Just by looking at it, you know it's not zero. So if your problem picks zero, you know it's off. You know the weights are off, right? I think he was talking about like manually coming up with every single number in the situation to just really, as a thought experiment, to really understand what's going on, right? To really understand how hard it is to optimize all these numbers. And then, so this is for one neuron, right? This is like the function for one neuron. And what he was mentioning is like, what if you turned it into a vector, right? Vector, like right here, like a matrix with n number of rows and one column. And then over here, taking all the weights and turning that into a matrix. Remember U and X, right? From a matrix factorization that we did for the recommendations. It's basically the same thing right here. Like what you guys did before is like a subcategory of deep learning already, right? And he has a bunch of videos on linear algebra, which could help you understand things a little bit better. I recommend them all to you. I think they're really good. I think they're better than Khan Academy. All right, so, and then he also talks about adding the biases as a vector also. So everything as a vector. And then he summed the whole thing up into a function like this, right? So basically he just summed what we're doing over here into this function. Okay. All right, so, okay, cool, excellent. We have 40 minutes left. All right, so open up the activities I sent you guys. Now we have our own, the curriculum team made their own way of explaining neural networks. It's significantly less mathy, but I think having that background coming into these Jupyter notebooks will help you a lot. So open it up. And open up Intro to Neural Networks. Open up that Jupyter notebook. And let's spend 10 minutes going through it with your partners. So Intro to Neural Networks. 10 minutes, go through it with your partners. Remote students, I re-uploaded the zip file folder. It didn't have the images and the data in it originally. So just delete all of that and then use the latest zip folder. You're going through Intro to Neural Networks. Hey, remote students, can you guys see the images? Anyone? You should be able to see this image right here. Oh, wait, I'm sharing my screen. Can you see this image? Anyone? Huh? Oh, I mean, I was talking to remote students, but you should. They can see it?
They say yes, Luella and Angie said that
They can see the images? I mean, not on my screen, but like on their screens. Can you guys see it on your screens?
No, I mean, in the notebook.
In the notebook, they can see it on their notebooks?
Emily said no.
So no? Yeah, and you guys are,
Your screen has it, but their notebooks also have it.
that's what I'm asking, yeah. Do their notebooks have it? Okay, it looks like some people can see it. Did you guys use this, the Jupyter Notebook, like, did you use neural networks.zip? Daniel, do you see the images? No?
There are
Oh.
no images in the
Oh man, where are the images? What do they do?
Can you
Open.
see in the markdown cell?
Ah, it's in an images folder above it. Ah, sorry guys. Damn it. Try 3. Neural networks. I'm sorry. I just assumed they were in the resources folder, but they weren't. I am so sorry. Try this one. It'll work. It was just 6 minutes. 6 minutes of trying to open it. Sorry. This won't work. Did it work? No?
Yes.
Cool. Excellent. All right. All right. Now, Chris, do you have it open? Daniel, do you have it open? Image is working? Johnny?
Getting
Okay. I'm going to wait like a Wait till Johnny and Chris say yes. Give me a thumbs up. Okay. That was pretty cool. I mean, if you're assuming it, then your median is also. Yeah, but it's a standard normal distribution. Now it's in be a normal distribution. It's probably a normal distribution, but not standard. Standard normal distribution is centered around 0, right? Right, yeah, it's a standard normal distribution that's centered around 0, right? Yeah, scale that. So it is in that. But no, it's normal distribution. You assume normal distribution.
Yeah, where it's centered around the. Yeah. Right. I was kind of just think of that bell curve. Like, that's.
So you have 75 to 75th percentile. It'd be cool if he gave you the 67.5 percentile. Right, because then you'd be like, oh, one standard deviation.
I'm nothing.
You should do it that way. You should do forward just so. Oh yeah, that might be the way to go. Because it might have just been typed out. Don't know what to do. All right, so Chris, you have it open?
Yeah.
Johnny? You guys were supposed to give me a thumbs up.
Oh,
Yeah, thanks. All right, starting 10 minutes. 10 minutes. Go over this notebook. Shouldn't be that bad compared to the video you guys just watched. Notice the difference between regression and classification. Go over it with your partners. All right, 5 minutes left, guys. This is called TensorFlow Playground, and this is really awesome. You could try out different machine learning models like without any code at all. Just try them out in TensorFlow Playground. You could even try out a neural network and kind of visualize what's going on and see the output visualized over here. So great thing to play around with while you're learning. So I advise all of you to check it out, fool around. You could also test out different machine learning models and see how they affect data and what the training error and testing error is for each one. How regularization affects the error. Here they're using TANH. We're going to use ReLU mostly for our neural networks. About 3 minutes, 40 seconds. And then we're going to move on to the logistic regression. Instructor logistic regression.
Yvonne, I don't understand what this activation thing is, because here's sigmoid again, right? What is this?
Oh, it's an activation function. So we use sigmoid, but that's not normally, that's like a simple version. So what we did was like it's not simple by any means, but the basic example of neural network, what that guy went over was a sigmoid function. So you can use a ReLU function. You can use different functions.
Does that stand for something?
It's a different type of function.
But when we did the movie rating, do we have a function for activation?
Do we use a function for activation? No, we didn't have an activation function. No. Yeah, we didn't have any activation functions.
Does that mean we had no hidden layers?
We didn't have hidden layers. Remember what we did? We just put random numbers in from a standard normal distribution, and then we kept optimizing it based on the cost function. We didn't optimize the numbers, right, based on any function. We got a cost function, right? We got a cost function. We optimized the cost function so the way so that it would be so the gradient was smaller. So that way, we were basically guessing random numbers in the beginning from the standard normal distribution, having a cost function, reducing the cost function to optimize those numbers, those missing numbers. And so the cost function was a big deal of it. That's actually how the backpropagation does work, though, of the neural network. Gradient descent.
I mean, that's still the matrix in the
It's certainly different, but it's certainly classification to a degree because like it's saying whether you're gonna like a movie, like what movie are you gonna like, right? Like what movies are you gonna recommend? So it's basically classification, not regression. That problem.
That has fixed labels, right? And in this problem, our system does not know the possible input values.
It does. The images. That's input, and that's labeled. You know what they are. It's not like you're taking random pieces of data and kind of grouping together.
Does it matter if we're regression versus classification? The type of activation you use?
It certainly could. In Keras, it normally uses ReLU.
Too many words don't sound like words.
Yeah, so you normally use the ReLU function. Keras is different because
What is Keras?
we'll go over it more on
So
Saturday.
Keras is like a language that I guess would be like
Language.
yeah, so like Keras and like TensorFlow,
It's
right?
Python.
They're
It's
like
library.
the
It's
tools
library.
you use, like a library to do like a neural net. The basic like architecture of like a neural net is like that little mappy looking thing. You have your inputs, like let's say in this case like images, right? And which is really like a matrix. And what you do is, let's say for like.
Okay, you want to speak up here?
So, okay, so just like in a very like basic sense of like what neural nets are, you have layers, okay? So first is obviously like your input, right? Your images, words, numbers, whatever. That's your input. And usually it's a matrix, some numerical thing. And you pass it either through like activation function or like a filter or like a convolution. Let's say a convolution neural net, like a CNN. CNNs are usually used for like images. And so you get from that, once you pass it through this like nonlinear function, okay? And that's what ReLU is. ReLU stands for rectified linear unit. And all it does is it basically just calculates a number. It returns a number. Okay. So you pass like your input through a nonlinear function, and it gives you like an activation number. Okay. That activation number now becomes the next input for your next layer. Now, besides your input layer and your very last like result layer, everything else they just call like hidden layers. Okay. Just kind of like what they were doing in Instacart, right? Like they just said, hey, here's hidden layers, right? Like they didn't really talk about, he didn't really go into detail like what's in it, but that's kind of what's in it. Basically, it's like matrices, you pass it on to a linear function, it comes out with more inputs, it goes to the next one, goes to the next one, goes to the next one.
Is each one a function? A non-linear
Yes, you keep
function?
passing it through a nonlinear function.
So it has to be different functions, like for example, one can be sigmoid, one can be.
Right. So usually, like they use, seems like ReLU seems like in fashion these days. I think performance-wise, like a lot of papers are coming out like ReLU is like doing well. ReLU is usually basically, and it's actually simpler than it is. All it's taking is it's taking the maximum between either 0 or your calculated number from that input. That's it. It just chooses which one is maximum. Takes that and then takes it. Like you keep doing that layer through layer through layer. And what happens is, like usually like in images, what happens is, so you have an image, let's say a person. But early layers usually detects things like edges, shades, colors, those kinds of aesthetics. I don't know how layers do it necessarily, like I'm not like an expert in this. But basically you can see as you go through all these different layers, it starts picking out these kinds of different features from the images. And in the end, you usually pass it through, if it's a classification, you pass it through like a softmax function or the sigmoid function. They're different. They're kind of similar in a sense of like it squishes your results to either a 0 or 1. Okay, so that's what the sigmoid function does. So if you're doing a binary classifier, that's great, right? Because you can interpret those zeros and ones. Because if it's a 0, it's not that image, maybe it's a cat. If it's a 1, it's a dog. You know, let's say those are the two classes that I have. So when you're squishing sort of your final results, which is maybe like a bunch of numbers, but when you pass it through a sigmoid function, any of those numbers becomes a 0 or 1, which now you can interpret, right, as either a dog or a cat. So that's kind of like the basics of what happens like in a neural net. And usually sometimes, like they say, it's kind of like a black box in the middle, because it's kind of true, right? Like you have these inputs, it passes through functions, it spits out an activation number, and it goes through another layer and keeps doing that until it sort of like the neural net detects kind of these properties of that image that you might not like necessarily be able to manually do. And then the end, that very final, either softmax function or sigmoid function, kind of gives you that interpretation of what those like final numbers are. So that's like kind of, I mean, yeah, it's kind of like deep learning is like super like fancy right now, but it's kind of it's been around like since like the 50s or 60s.
It was
It's just
invented
that-
like a long time ago, right?
yeah, they've been around. It's just that I think now hardware is kind of able to actually do these kinds of computations. Because when you think about it, images are huge matrices, right? And that they're actually like multi-dimensional like matrices. Especially like colored photos. You at least have 3 layers, right? That blue, the cyan, and the yellow, whatever, you know. So think of it as at least like, you know, like by 3 layer, you know, let's say 100 by 100. So you're processing like sort of all those kinds of combinations in an image.
Awesome.
Sort of help with the language. So you use, so the popular things right now is Tensor and Keras and maybe PyTorch as like the language you use to implement a neural net. Deep learning is just in general sort of what they call all those different neural net algorithms. So you have things like convolutional neural nets, recurrent neural nets, like all this other stuff. And then, but the architecture, and when they talk about the architecture, it's just talking about how many layers are in it, what kind of activation functions are in it, and maybe like how you're sort of like, again, the gradient is still used here when you're like changing those weights. So it's the same still dynamics of like you're optimizing some kind of weights through like gradients.
That was amazing.
I'm trying to like find this like YouTube video that like was shown to me before, and I thought it was
Aw,
so unlike.
somewhere in your
If I
history of
find it, I'll,
your
like,
history of cat videos and
oh, there's so many.
data science videos.
So good.
So so TensorFlow actually it's pretty cool because it'll boil down to C code, which runs really fast, but you write in Python, invented by Google, made for you to make, made for deep learning, and then Keras. But the syntax is there's a lot of syntax to know because you're actually defining every little thing in it. But it also comes with this visualization thing called TensorBoard, which we'll actually use. And you could actually visualize your neural network all in the browser. It'll like do the whole, it'll show you everything. So this guy came out with Keras, and Keras is built on top of, it's almost like it's a Python library, and it converts into TensorFlow code. But it makes it very simple. It makes it very, very simple to create a neural network, define what type of function you want to use, right? And then define how many layers. And every time you want to add a layer, it's basically 1 line of code. That's it. And you could use it to predict after you add the layers that you want to add. And it'll convert it down to TensorFlow code for you. All right, so
You said it's built on
so it had, you could choose like what backend you could have. Like you could choose either Theano or TensorFlow, both deep learning frameworks. Both, I mean, Theano was heavily used for a long time, and then TensorFlow came out by Google, and recently Keras like dropped support, like I don't know, like 3 or 4 weeks ago, dropped support for Theano. Not that it's bad. I mean, it's fine. It actually, you won't probably see any difference between the two on a small data set. On a probably really big data set, I mean, TensorFlow would probably be more efficient, faster. That's what Google uses for their backend stuff, machine learning and deep learning stuff. Good questions. All right, so let me see here. I can show you one thing before you leave. I do want you to take a look at the logistic regression, but look at it later. Let's open up, let me see here. Stu Sleep Deep. Stu Deep Sleep. So
Just see,
Stu Deep Sleep.
I
Is it inside the Stu Sleep folder? There's 2 files in there inside the Stu Sleeps folder. There's Stu Sleep and Stu Sleep Deep. Stu Sleep is without a neural network. I forget what do they use? Do they use the linear model? They use linear regression here for the same problem. They use linear regression, and then in Stu Sleep Deep they use a neural network. So let's take a look. Open up Stu Deep Sleep. Do you have it open? You're gonna go into deep sleep in here. All right. Boiling down to, we split our data into training and testing, just like before. Scale our data sets, our training and testing data, and then over here we're going to import MLP regressor. This is not TensorFlow. This is scikit-learn. We're going to import MLP regressor from the neural network portion of scikit-learn. And then we're going to pass it 1 layer of 30 neurons right here, 1 layer. So if you put multiple, right, this is a tuple, right? If you put multiple numbers here, that's multiple layers. 30 neurons. Yeah. And then max iter is the number of times, the number of iterations that it does to optimize the weights. Random state, you guys know. And it creates our model over here. And then just like before, just like always, we're fitting our model to our training data set, right? So we're fitting our model to our training data set. What does anyone remember what Ravel does? It flattens the yeah, perfect. Good job, Manu. It flattens the array, meaning if there's a multi-dimensional array, it'll take the multi-dimensional array, turn into 1-dimensional array. Okay, so over here, we're calculating the R2 score. Go ahead, Manu.
I thought for a model, you always need, so for example, if X is, the shape of X is a tuple, right? And the first is number of rows and second is column. Right? Number of features, let's say.
Yeah. So if you do the shape, of something, then you'll have the
X and Y need to have the same shape.
X and Y. No, they don't. The same rows, right? Same rows, but not the same. The columns have to be different, right? Because you're gonna have 1 column for Y, 1 output, and you're gonna have like maybe at least 1 feature, 1 column for X, but you probably have like 2 or 3 features or 4 features maybe.
So instead of reshape, you could just do
If it's an array. If it's a list, then you could do Ravel.
It's always a list, but in Y, it's always like.
Yeah. You could do Ravel. You could use Ravel to convert it to a 1-dimensional array. When you're feeding it in, it has to be a list within a list, right? So that's why we do reshape, right? That's why we're doing reshape. But in this case, we did Ravel because we just wanted it to be 1-dimensional over here. And then you calculate the score, and we get the score over here, right? We get the training score is 0.95, and we get the testing score 0.71. So maybe we could get that down, and we can get the test score better, closer to 1, if we increase the number of layers. So what if we add in 30, 30, 30, 30, 30? You know, maybe that does it right there. Maybe our testing score goes up to closer to 1.
Oh, so that's like how many dots we have in the first layer.
Exactly.
So we only have 1 layer.
Right now we have only 1 layer. Yeah. So this isn't deep learning. As soon as we add in 1 more layer, which is literally 2 more characters, we're doing deep learning in this right?
Then earlier you said, we're doing one layer of with 30.
Yeah, exactly. So when we did right here, this is one layer. You would just add in another 30, and then we're doing deep learning, essentially, because we have 2 layers.
So in the last part, when we are adding the layers, 30, 40, 30, so that means 30 neurons and 40 layers.
Where do you see 40 from?
Can you go down? Where we are making the second model. Down below. Further down.
Really?
The last cell. Yeah, this one.
Oh yeah, in this example where we have 3 hidden layers. We have 30 neurons, 40 neurons, and 30 neurons.
Oh, so it's always the number of neurons.
Yeah.
And the oh.
It's not the number of layers. Yeah,
Misunderstood.
yeah. So it's number of neurons in that layer. So 30 neurons in this hidden layer, 40 neurons in this hidden layer, 30 neurons in this hidden layer, right there. And it's kind of nuts. So like you look at this and you're like, the code isn't that bad. I mean, the understanding of it's important. And you saw how hard that was, right? But in implementing it isn't actually that bad. It's just like remember that graphic of artificial intelligence, machine learning is part of it, and then deep learning is part of machine learning. Like you see, deep learning is very much just machine learning.
Why don't you always just have multiple layers and many neurons?
That's a good question. So maybe it takes more memory. Maybe adding in the extra layer doesn't actually increase the test error at all, or maybe it increases it. Maybe it's so little that it doesn't even matter. Maybe you're happy with the predictions that it's giving you, so you just do one layer instead. So remember when I said. So it's not overfitting. It's like it's just like it's like, let's just say it's overkill at that point. So like if it just increases it by 0.001 and you're looking for an R2 score of 1, it's like it doesn't really matter that much, right? So if you add another layer and it doesn't do much, then you might as well delete the layer.
Unless resources
Unless yeah, but that's adding to global warming, right? Yeah.
In real life, real data, these networks take long time to run and
yeah, so that
CPU power.
you're right. You're absolutely right. So that's why that's the exact reason why GPUs are more. That's why NVIDIA's stock is going up, and AMD's stock went up a lot because of deep learning, right? Of all the deep learning that's happening, but also because of cryptocurrency mining. It's probably more of the cryptocurrency mining than the deep learning, but like deep learning is definitely contributing to it, right? I mean, people are doing it and using it a lot for different things, and that's why their stock's going up. But the whole thing is like, we have an example here. We don't have time to go through it. If you guys just run all and walk through it, this is the linear regression. This is a linear regression model right here. It's the same problem, but using linear regression. And the thing is, it's interesting because this is much cheaper, right? So you can calculate the R2 score. Is it worth it? I mean, you could look at the scores and see, like, is it worth it? You got the testing score was 0.74 over here. And the testing score over here was 0.8 with 3 layers. That's actually a pretty significant difference. 0.06. 0.06. That's a significant difference. So then, like over here, a good R2 score is 1, right? So we got it closer to 1 in this case. So if this matters to you that much, then you should use it. You should use deep learning. If not, then if you're happy with the results from your linear regression, you should obviously just use linear regression. It's going to be cheaper.
It depends on your value of your output.
Yeah, if the output's fine. Like let's just say you predicted something, and then it was like basically it, and you're like, that's good enough. Then just go with this instead. Because as you have to also think about the computing power and the resources.
Yes,
Yeah.
exactly.
Yeah.
It just depends on how accurate you want the prediction to be.
Yeah. So like as Kat mentioned before, an art, right? If it works, then
But,
good.
so for
sorry, Teddy. Yeah.
Oh.
Oh, can Teddy go?
Yeah,
He's been waiting. Oh, sorry, Angela.
Going back to Nolan and
Which one?
students.
Oh, this is just Stu Deep. Okay.
So on the bottom, I see that you're using, there's 3 layers, but what's the purpose of ramping up from 30 or 40?
Just like whatever.
Okay. So
Yeah.
there's not like a specific.
There's no like right answer to it. I mean, like, maybe there is a right answer. I'm not gonna say I just don't know it. And that I think that guy, like every book I go to, it's like they talk about how just guess and then see if the error is good or not. Maybe a mathematician would be different if I paid attention my math classes. Yeah. Oh, Angela, what were you saying before?
I have 2 questions.
Yeah.
So, start on Teddy's question, that 30, 40, 30.
Mhm.
So in that 3 blue, 1 brown,
Mhm.
you use like 16 or something, right? Is there some way to know what the default to start with should be?
He just said he randomly chose 16.
Right.
So we just
Is
randomly
this-
chose
is this
30.
random?
We just randomly chose 30.
And then for deep learning, we can improve the model by changing the number of layers in the neurons.
You could add more layers.
Right?
So what if we added 30 layers here? And what if the R2 score went to 0.9? That's awesome. That's great. That means like the layers helped.
For linear regression,
Yeah,
the only thing you can do is add more features that could help
you can modify the features. You can modify the features.
scale it.
You could scale the data differently, right?
So scale it differently means
I don't know if the
there's
scaling,
one-
Kat, does scaling the data affect the R2 score?
Definitely, probably for like other algorithms. I don't think it matters as much maybe for like
Oh, what about linear regression?
The activity said it doesn't. If it's only one feature.
If it's one feature, and well, that's what the activity said before. It's one feature,
If
and
you have one feature, then you're not really like I said, it's not like you have an age and salary type.
No, but my example that I
Yes.
take care, John.
I mean, it could also be.
No, not my example, but
Yeah, yeah.
just think about
Oh,
You can always just.
no.
But wouldn't you do all that data manipulation
Under
for
this.
deep learning
No.
versus linear regression as well?
Yeah, you would do. You would scale it no matter what.
Model-wise, the only thing you could
No.
really do for linear regression
Is import something different.
more data.
Yeah, I guess like having more data,
Something.
right? Like generally you want to have 10x the data, or maybe changing up your data set. So remember like the pool size, we're changing that up to a Boolean instead, and then changing up like the hot encoding, which I mean is super easy to do with the dummies thing.
I also thought that linear regression is more like finding for predicting for continuous variables, and the deep learning is for
Classification.
So
Classification.
That's the major difference.
It is, yeah, it is. I mean, you see regression in the name. So yeah, it definitely is that way. In this case, what was the data set for this? Stu sleep. Like what was the X and Y? Let's take a look at this. So we had body weight, brain weight. This was X, right? And what was Y? Y was the brain weight, right?
Yeah, so X is like 9 features, and Y is just the total feature.
A total sleep. Okay, so total sleep.
It's continuous thing. It's not classification.
Yeah, in this example, we used it not in a classification way. You can use it for regression, but generally you don't use it for classification.
The regression rates.
No, I mean like for neural networks. I mean,
No.
generally you'll see the applications for it being classification, generally.
So that's what I was thinking.
But you can use it. You can. Like we just demonstrated, you can use it for regression, but in most situations you
So
can.
we were talking about the Y
Yeah.
part, right?
The Y part.
Yeah,
Mhm.
followed by like she was asking to buy an regression. Then the ways to improve the model.
Mhm.
But I was like, regression is mainly used for continuous variable.
Yeah, it's going to be used for continuous. We do have an example with logistic regression though, where it's more of a classification. So if you take a look at the INS logistic regression, it goes into the classification, like clustering it, splitting the data set, and using zeros and ones to represent the categories. I hope you're inspired to learn more, and
Yeah.
hope you're, obviously, but I mean, but
I'm just trying to understand everything so I can implement it in my project.
hmm.
So I've just started, but everything is all right now. So that's why I'm trying to understand how to
Sure. Well, if it predicts the values, that's good. If the error is low,
No.
if the error is high, error is really high.
100,000.
100,000? Wait, is that an R2 score?
No.
Because that's not possible, right?
MSC.
MSE? Well, then rescale your data.
That's what I'm
Yeah, cool. Well, forget the MSE. Try the R2 score.
1 to 1 for 1.
Okay, all right.
Yeah, I know. So,
All right, see you guys Saturday.
But, it looks like
Take care.